Good afternoon, everyone. So welcome to my YouTube channel, Math of Now. So today we are going to see 28th lecture on Riemann integration. So let's start today's session. In uh, in the playlist, in the playlist, uniform convergence of function. The playlist uniform convergence of functions. We have studied Abel's lemma. Okay. Abel's lemma. We have studied Abel's lemma. Okay. So we recall Abel's lemma. Okay. What is Abel's lemma? Let Bn be non-negative monotonically decreasing sequence and small k and capital K are infimum and supremum respectively of the sums summation I goes to M to P U I goes to, so this is I goes to M to P for P is equal to M plus 1 and so on up to N. Then what we have? Then Bm small k less than equal to summation I goes to M to N U I B I less than equal to Bm capital Q. Okay, this happens. Okay. In particular, if M is equal to 1, then B1 small k less than equal to summation I goes to 1 to n ui pi is less than equal to p1 capital K. Okay, capital K. So this is actually Abel's lemma. We have already proved this lemma in the playlist uniform convergence of function when we studied Abel's lemma. Okay. So you can see that playlist and you can see its proof if you want. Okay. So you are here. Okay. Now we will prove a result due to Bonnett's theorem. Okay. Let Z be Riemann integrable over closed interval A B. Okay. And phi closed interval A B to R be non-negative monotonically decreasing function. So monotonically decreasing function, then there exists xi belongs to closed interval A B such that integration A to B phi g is equal to phi A to xi gx dx. Okay. So let's see its proof. Okay. So phi from closed interval A B to R is non-negative monotonically decreasing function. Okay. We know that monotone functions are Riemann integrable. Therefore, phi belongs to R A B. Since f comma phi belongs to R A B implies phi G belongs to G and phi belongs to phi and G belongs to R A B implies phi into G belongs to R. Okay. Next, now Let M and capital M be supremum let P is equal to AX naught, X1, X2 up to Xn is equal to B. Be a partition of closed interval AB. Okay. Put let Mi is equal to supremum of G on Xi minus 1 to Xi. Okay. And small mi is equal to infimum of G on Xi minus 1 to Xi. Okay. Now, mi is less than Tx is less than capital Mi for x belongs to Xi minus 1 to Xi. This implies Mi delta Xi is less than Xi minus 1 to Xi. Gx dx is less than equal to Mi delta Xi. Okay. Okay. So let's say it 1. So let's say it 1. Okay. 1. So let P is less than equal to, then we get summation I goes to 1 to P Mi delta Xi less than equal to, what is this? This is A to, we are taking summation. So this will become A to XP Gx dx. We are taking summation. And when we take summation of this integral, the initial point is A, then it will be final point is XP. I goes to 1 to P Mi. Let's say it 1. Okay. Next, choose T1 is equal to A choose choose Pi belongs to xi minus 1 to xi such that P1 is equal to A, okay, and Ti are arbitrary for I goes to 2 P up to N, okay. Then Mi less than Fti less than capital Mi. This implies Mi Fti delta Xi Mi delta Xi. Okay. Now taking summation, what we will get? Taking summation, what we will get? So this is G actually, sorry. This is not F. This is G. This is G. So this is G. This is G. Okay. So what is this? Now we are multiplying with delta Xi. Now taking summation. Okay. So taking summation. Okay. Taking summation, what we have? So taking summation up to P. Up to P. Summation. I goes to 1 to N. Capital Mi delta Xi. Okay. Let's say this 2. So this is P here. So from 1 and 2, we have from 1 and 2, what we have? We have summation I goes to 1 to N. Sorry, P. This is P. This is P. Small mi delta Xi that is less than A to XP Gx dx, and this summation also I goes to 1 to P G Ti delta Xi less than summation I goes to 1 to P capital Mi delta Xi. Okay. So their difference will be also less than, because these two inside quantity lie between this summation and this summation. So their difference, it means we have summation I goes to 1 to n g di delta xi minus summation a to xp gx dx dx is less than equal to this summation this is p mi delta xi minus summation I goes to 1 to p mi delta xi this. Okay, less than equal to this. Okay, but so this implies, so I am writing it again. Actually, I want to write in a proper manner. Let it write it again. Let's write it again. So this implies, summation I goes to 1 to and sorry p g ti delta xi minus a to fp g d dt or you can write x here. Okay, no problem. Write it x here. X dx is less than equal to I goes to 1 to p capital Mi delta xi minus summation I goes to 1 to p small mi delta xi. But this is nothing but this is equal to summation I goes to 1 to p mi, okay, minus mi delta xi. But inside this thing is non-negative. Inside thing this is non-negative, so this will be less than equal to I goes to 1 to n mi minus small mi delta xi. And what is this? Because inside thing is non-negative, if I can add the more quantity here, I can increase the value of it up to n. So this will be more, okay, because inside thing is non-negative. So what we got actually? What is this? What is this? I can expand this. I goes to 1 to n capital Mi delta xi minus I goes to 1 to n Mi delta xi. What is this actually? This is UPF, this is UPG, and this is LPG. This is UPG minus LPG. So what we have? So this implies summation. This implies summation. I goes to 1 to P GTI delta xi minus summation P to xp gx dx is less than equal to UPG minus LPG. Okay. Okay. So what we have actually, this implies A to xp gx dx, okay, minus UPG minus LPG, that is less than equal to summation summation I goes to 1 to P GTI delta xi, that is less than A to xp gx dx plus UPG minus LPG. Okay. So let's see it equation number 2. Since G belongs to RAB, since G belongs to RAB, since G belongs to RAB, G belongs to RAB, we get that Gx, the function Gx, the function A to x Gx dx is continuous on AB. So continuous function has bounds, so this implies there exists K1 and K2 such that K1 less than equal to A to x Gx dx. Okay, and this is, so I can write T here. Okay, no problem. No problem. I'm writing this K2 for all x belongs to closed interval K. From 3 and 4, from 3 and 4, we get what we get. We get what was this? This was integral A to xp. So from From 3 and 4, what we get? We get in place of integral a to gx, we can take lower bound, this one, a1 minus upg minus lpg. That will be less than equal to I goes to 1 to n, sorry, p p p and gti delta xi summation k2 k2 plus upg minus lpg. Okay. So here in above, I have taken T1 is equal to A. That is not actually needed. Such that Ti are arbitrary for I goes to 1 to up to n. Okay. Up to so now you see that. So this is fixed. So I am calling this part K, small k. I am calling this part capital K. So this implies A less than equal to summation I goes to 1 to P GTI delta xi less than capital K, small k, for P is equal to 1 to up to n. So now, and okay. So it is actually required. In earlier, I have erased that T1 should be 1. Actually, it is required. Okay. So I made it. I should write there are such that T1 is T1 is A and Ti are arbitrary for I goes to 2 to n. 2 to n. Okay. Now this is this and this sequence phi Pi I goes to 1 to n is non-negative monotonically decreasing sequence because phi is non-negative, monotonically decreasing function. Okay, that is why this becomes a non-negative monotonically decreasing sequence. Now by Abel's lemma, we get what we get, this summation, this one, phi t1 times into this small k. What was small k? Small k less than equal to summation I goes to 1 to n. Okay. So G T I phi T I delta X I summation phi T1 capital K but capital small k was dot, you put the value again, so this implies what is T1? T1 is 8. Okay, T1 is 8. And what is this K1? This is small K1 minus UPG minus LPG. Okay, this was this. That is summation less than I goes to 1 to n GTI phi TI delta XI. Okay, and this less than this is less than phi A. What was that? This was K2 UPG minus LPG. Okay, this one, this. Okay, now one thing. So I am taking here where K1, K2 are, where K1 is infimum of A to X GX and K2 is supremum of the function A to X GX function. Okay. So these are infimum and supremum over closed interval AB. Okay. So let's say this equation 5. Let's say this equation number 5. Since G RAB, we get limit non-free tending to 0, UPG minus LPG is actually 0. Okay. So letting non-free tending to 0 in 5, we get. So what is this? This is phi A So when norm tending to 0, this will be K1 and this will be UPF minus LPF will be 0. This is, and this is in equation number 5. The middle thing is nothing but Riemann sum. This is nothing but Riemann sum. So both the function g and phi are Riemann integrable. So it will show, it will convert to A to B phi g. Okay, x dx. That is less than equal to phi a k2 minus 0 plus 0. So what we have, phi a k1 less than equal to a to b phi x gx dx is less than equal to phi a k2. Okay. So okay, now there are, now let's say equation number 6. Now either phi a is equal to 0 or phi a is equal to positive, because function is non-negative. So either this will be 0 or this will be positive. It cannot be negative. So if phi a is equal to 0, from 6 we have from 6 we have, so what we have from 6, from 6 we have 0 less than a to b phi x gx dx, that is less than 0. This implies a to b phi x gx dx is 0, which is actually 0 to phi a to chi gx dx. Okay, for any chi belongs to closed interval a b. Okay. So we have in the case phi a is equal to 0, the result is true. It means a to b phi x gx dx is equal to phi a to chi gx dx. This result is true. You can take any chi belongs to closed interval AB. Okay. You can take any chi belongs to closed interval AB. Now, if phi a is greater than 0, dividing both the sides of 6 by phi a, we get k1 less than equal to a to b phi x gx dx upon phi a that is less than equal to small k. Okay. Now, now here, now this value k1 is infimum of g. Okay. But k1 and k2 are infimum and supremum over supremum respectively. Supremum respectively. Respectively of the continuous function of the continuous function a to x gx dx. Okay, dx over closed interval a. So k1 and k2 are supremum and infimum of continuous function, and this value integral upon phi a is in between k1 and k2 by intermediate value theorem. By intermediate value theorem. By intermediate value theorem. There exists xi belongs to closed interval a b such that a to b phi x gx dx upon phi a will be attained by continuous function. So this xi by intermediate value. Middle thing will be attained. If you take any value in between supremum and infimum, that will be attained by continuous function. Okay. Okay. So this implies a to b phi x gx dx is equal to phi a to b gx dx. So if phi a, so if phi a so if phi a is greater than 0, we get xi belongs to closed interval a b such that a to b phi x gx dx is equal to phi a to b gx dx. Okay. Hence, in either case GA is equal to 0 or phi a greater than 0. This is phi is 0. We have a to b phi x gx dx is equal to phi a to j gx dx, or some j belongs to closed interval. So theorem is proved now. So finally, theorem is proved. Okay. So we have shown, we have proved Bonnett's theorem for Riemann integrability. Sorry, Bonnett's theorem for Riemann integration. So today's lecture up to this. If you have any problem related to this, you can comment on my YouTube channel. Like, share, comment, and subscribe my YouTube channel. Thank you very much for today's lecture. Thank you very much.